Welcome everyone to today's colloquium. My name is Chen, and I'm a condensed-matter theorist in physics. And I'm very happy that we can have Haruki Watanabe from University of Tokyo here today. Well, not here, but in Tokyo, on Zoom here today to tell us about his work. So let me introduce Haruki a little bit. So Haruki is a condensed-matter theorist at Tokyo, and I overlapped with Haruki when he was only a student, and I was a postdoc. We were at Berkeley in the same group. So I learned of Haruki's work from a very early stage, and I always find that his work brings a higher level of clarity to the problem at hand. For example, one of the earlier work he did was on the topic of time crystal. And at that time, people were contemplating a very intriguing question of whether it is possible to spontaneously break time translation symmetry and what that means. So it was quite confusing for a while whether that works or not work. But Haruki was able to put a final word and proving that if it's continuous time translation symmetry, then it doesn't make sense to talk about breaking it. But then it opens the possibility of having a discrete time translation symmetry, and that can be spontaneously broken, and that is what people talk about in terms of these time crystals nowadays, which is also a big topic. So as I mentioned, Haruki was a graduate student at Berkeley. Then he went on to a Pappalardo fellowship at MIT as a postdoc. And then very quickly he moved back to University of Tokyo, where he's now an associate professor in the University of Tokyo. So over the years, Haruki has worked, done a range of work. And another one that I want to highlight to you is his classification of topological band structures in materials. And if you look up his publication list, there are papers about complete classifying band structures with 230 space group and 1651 magnetic space group, and he did it all. But this is way more than just hard work and going through all these symmetry groups, because again, Haruki, while he was doing that, he one thing I found particularly nice is that he was able to clarify a very tricky notion regarding fragile topology, which is again something that confused people and people got wrong. But Haruki was able to clarify that there exists this thing called fragile topology, that something looks like it's non-trivial, but actually it's trivial, but it's also non-trivial. And only so he was able to by pointing out that it clarifies a lot of phenomena that we observe when we study band topology related to topological insulators in particular. So because of his work, Haruki has been awarded various awards, including the Young Scientist Award of the Physical Society of Japan, the Yukawa Memorial Prize, and the Condensed-matter Science Prize. So today, Haruki is going to tell us about one of his recent work on multiple moments, quadruple moments, octuple moments in particular, and how that can show up in things as common as table salt. So I guess after the colloquium today, we can all go to the kitchen and do some experiments. Okay, so without further ado, please take away, please, Haruki.
Thank you. Thank you so much for the very beautiful introduction. And I also want to say, many of the works she introduced is done in collaboration with many good researchers like Adrian. He's also was an Aswin student. And also like today's talk is done in collaboration with my graduate student, Seishiro Ono. I guess he will start looking for a job soon, so he will be a good candidate for a postdoc in the United States or abroad, I guess. Okay, so let me start. So as you know, like there are infinitely many number of material in condensed matter physics. For example, if you look at periodic table, there are many elements. Also, their combination produces this list of complicated compound, and they have different symmetries. So we want to have kind of unified scheme of classification, right? And so classification of so for simplicity, let me assume zero temperature. And I want to focus on systems that can be described by Hamiltonian with symmetry group G. So in this case, like we first ask, if symmetries are broken or not. And if symmetry is broken, it's ordered phase. If it's not broken, it's disordered phase. So this was, like a classical Landau paradigm of classifying phases. This symmetry breaking pattern G to H characterizes the phases, right? But more recently, like we have advances of further classifying phases. Like we first ask existence or absence of excitation gap, if it is gapped or gapless. And then we look at degeneracy for gapped systems. If degeneracies are completely accounted by a symmetry breaking pattern, it's kind of trivial phase. And if it's not, if there are more degeneracy than those expected from symmetry breaking, then it's like a long-range entanglement phases. And these long-range entanglement phases contain, for example, like a fractional quantum Hall state or quantum spin liquids, or more recently, people discuss fractal topological orders. So this is exciting. But today, my topic, my focus will be on this, short-range entanglement phases. So that includes trivial phases or topological insulators and symmetry-protected topological phases. So how do we classify short-range entanglement phases? So we assume symmetry group G and excitation gap delta. And so we kind of identify Hamiltonian with the classification of Hamiltonian with classification of the ground state, right? So here we say H1 and H2 belongs to the same phase if they are connected without breaking symmetry or without closing gap. And there's a subtlety regarding whether or not we allow for adding ancillaries. This is related to like a fragile topology, but for now let me forget about that. So we ask they are connected or not. So if you increase symmetry, for example, let's consider symmetry G prime, that is a supergroup of G, then that additional symmetry will have two effects. For example, it will put additional obstruction of connecting two different phases, so it enriches the phase diagrams, or it can prohibit some phase that existed for symmetry group G. For example, like Chen insulator will be prohibited by time reversal symmetry. So it has two effects, enriching or reducing phases. So classifying all possible phases under symmetry group G is a difficult task. But recently, like over the last 10 years or so, people worked on it very hard and have better and better answers to that question. So in these phases, some of the phases contain product states, and I would say, trivial phases are those connected to real space product states, and topological phases are not connected to real space product state. That means, you must have some residual, like removable quantum entanglement. So that's topological phases. And so topological phases usually exhibit a boundary signature. So that's called bulk boundary correspondence. So for two-dimensional topological insulator, there's a well-known helical edge mode like this, right? And so this is a Chen insulator. So Chen insulator have helical edge mode. D2 quantum spin Hall insulator have helical edge mode. So these there are edge modes in bound insulators. Even for spin models, so this is Harden chain, and S equal. So you have S equal 1 spin on each side, and they interact with each other. So in this model, although we start from S equal 1 model, the edge supports S equal 1/2 spin. So this is like an emergent fractional spin appears on the edge. So all of these works are kind of an example of bulk correspondence between bulk topology and non-trivial boundary. Non-trivial boundary are usually boundary states. States here means it's like degrees of freedom. You can do something on the edge. For example, for the spin model, you can flip the sign, direction of this spin. This is spin up and down, 2 degrees of freedom here. If there's no state, if states are gapped, then the surface can be instead be like a topological order state. But this is not the topic of today's talk. So this is like a bulk and boundary surface correspondence. And more recently, people realized that surface signature can be localized to like a lower dimensional part of the surface. Like for example, this second order topology case, in this 2D system, reflecting the bulk topology, there will be zero mode at the corner. And this 3D system, that there can be 1D gapless mode on the hinge, or 0-dimensional 0 mode at the corners. So this is like an example of higher order topology in contrast to the traditional first order topological phases. And there are many examples, like I guess the simplest way of cooking up this example is to apply a magnetic field to an inversion symmetric 3D topological insulator. Then because magnetic field breaks dimensional symmetry, it opens the gap to the surface mode. But then there will be residual higher edge mode at the equator of the system. But even in the absence of magnetic field, people realize that, for example, the famous material like bismuth, even bismuth is higher order topological insulator, and there will be surface helical mode like this. So the message of this slide is that the boundary state can be localized to corners and hinges in the case of higher order topological insulators. By the way, you can ask question anytime, and please interrupt me if there's something not clear. Okay. So in previous slides, I explained boundary correspondence of topological insulators, but there is also another set of boundary correspondence. So that is for trivial insulators. And these notions are getting clarified in these recent works. And for example, in this paper, they discussed that in any fold rotation symmetric model insulators in 2 dimensions, that there can be a corner charge, and this corner charge is quantized into the unit of fraction of charge unit. So charge unit is E, and corner charge is like 1/4 of E, or like half of E, and so on. Okay. So although this is trivial insulator, because of this fractional quantization, there's still something topological here. And so in these examples, so multiple moment implies boundary charges, and these charges are frozen. So these are not degree of freedom, right? In contrast to the topological insulators. So they are modes, degree of freedom, but these are frozen charges. So there's a difference, but there's a kind of similar boundary correspondence. The most famous example of boundary correspondence of trivial insulator is the relation between polarization and edge charge. So let's assume U1 symmetry and translation symmetry. U1 symmetry is to have the notion of charge, and translation symmetry is to have the notion of like a unit, repetition unit. If you open up the textbook, classical ERW textbook, then it contains a formula like this for polarization. So for a given unit cell, you can compute the charge times position and sum over all charges in the unit cell, and you get some number. So this is the polarization at least for the classical level. And you compute polarization for the material, but if you have an interface of material and vacuum, then the value of polarization drops from px to 0 here. It implies the presence of polarization charge, and you can get this charge accumulated to the localized to the boundary or edge by this integral. So actually, edge charge is given by bulk polarization. So there's a bulk boundary correspondence. And so that formula was for classical particle, but we know how to do the same calculation for quantum mechanical systems. And that formulation is known as modern theory of polarization. To do that, we form periodic boundary condition. So periodic boundary condition identify two edges of the system at the level of creation operator of, say, electrons or particles in the system. You identify a creation operator at x plus L with creation operator at x. So this is the periodic boundary condition. So it effectively forms a ring out of this initial 1D system. So because of the U1 symmetry, we assume we have a concept of U1 charge, and it is given by given as a sum of local charge density. And using this charge density, you can form a polarization operator P. And basically, we want to compute the expectation value of this polarization operator. However, this operator P is inconsistent with the periodic boundary condition. This is because this integrand, you have x, and this combination is not consistent with this identification of x equals 0 and x equals L. So this naive expectation value doesn't work. However, we know the resolution. We can simply add this Berry phase correction to this classical formula. So for band insulators, we compute the Berry phase using Bloch wave function. And for interacting systems, we compute, again, Berry phase, but instead, in this case, we assume twist boundary condition. So we change the identification rule a little bit by introducing twist angle. Then compute this Berry phase. I think the basic idea of this formula is that, like a derivative of K is related to position of X in quantum mechanics. So it kind of, gives you the something related to position, right? So it actually works. So this is a modern theory formula of electric polarization. Then another formulation of polarization is called restart formula. So instead of computing excitation value itself, he puts this operator P into the exponent. So because of this, the identification of x equals 0 and x equals L is now consistent with this expression because it only changes this exponent by integer multiple of 2 pi. And actually, these two gives you the same answer, at least for one-dimensional system. So what I want to say is that we know how to compute polarization even for interacting systems. So this is good, and we know how to predict surface charge, right? So we want to do the same thing. So can we formulate bulk higher order multiples like quadrupole moment or octupole moment? And there are many attempts. For example, the first thing I will come up will be just generalize this Berry phase formula into this. Because this partial derivative of kx was x. For example, I can change it to this second derivative, so kx, ky. Then it will probably measure the x and y, right? But this combination is clearly gauge dependent. So if I change the phase of Bloch wave function, the result of this integral can be changed by an arbitrary manner. In contrast to this, Berry phase formula. So in this case, the change under this gauge change is only an integer amount, so it was fine. But this modified formula gets severe gauge dependence, so it doesn't work. There are recent attempts of generalizing restart formula. So instead of just putting px on the exponent, we can probably put this combination in the exponent. But then, again, this formula breaks the periodicity of the system. So if I want to identify x with x plus L for arbitrary y, right? Actually, this combination is not periodic, so it doesn't work. Okay, so this doesn't work, this doesn't work. And there are recent there's some recent work on computing something related to quadrupole moment, but from a different approach, like called nested reason loop approach. But this one does not give you the quadrupole itself or corner charge itself. And also, like the relation to these area works are kind of not clear. So what I want to do is to do more direct generalization of modern theory formula. Okay, there are many recent works discussing this point. So, goal of my talk today is to give a general formulation of bulk multiple moments, and this kind of help us classifying trivial phases of matter. So what I want to do is to, for given material, we compute this quantity, and it will predict the surface signature. So we want to understand the relation between these multiple moments and corner and hinge charges. Okay, and using this knowledge, we want to propose material and experiment. And as she introduced, the bottom line of today's talk is the corner charge of stable salt. And this is the most common material we have in the daily life. And what I want to discuss is that if I have a cube of crystal sodium chloride, we will have 1/8 corner charge at each corner. Any questions so far? Good. Okay, let me proceed. So before going to higher dimensional systems, let me discuss 1D system in more detail. So again, so I said there are correspondence between bulk polarization and surface edge charges. But there's some ambiguity in this formula, right? Here, even at this classical level, when we compute polarization, we need to assume some initial. So previously we take this initial, but I can take this initial as well. And depending on the choice of initial, the value of polarization changes by integer amount. And this is the same at the level of at the quantum mechanical level. Like very phase formula have integer ambiguity. That's related to choice of initial or choice of the phase of block wave function. Similarly, the edge charge also have integer ambiguity. So after computing polarization and predicting surface charge, edge charge, we can decorate the edge by bringing in additional charges from outside. Then it will change the value of edge charge, right? So in other words, you can change the position of the edge by changing the position of the termination. So edge charge also has an integer ambiguity, and that related to the choice of edge termination or decoration. So what I want to say is that this formula is consistent. Both sides have the same ambiguity. But so far, the fractional part of the polarization was arbitrary. So the surface charge can be like 0.1. But in the place of symmetry, the possible charge that can appear at the edge is quantized. So for example, let's assume inversion symmetry. So x goes to minus x. So in addition to U1 symmetry and translation symmetry we have. Then, because I said, like a polarization is defined only modulo integer. So this symmetry implies that polarization is quantized to either 0 or 1/2 in the range of charge E. This means that there are at least two phases under this symmetry, and they are not connected to each other adiabatically. So this periodic arrangement of minus E plus E charge, it will have polarization 1/2. And this side, the arrangement of neutral particles or even charge particles. So they also all belong to px equals 0 side. So naively, they are different, but you can split this 2e charge into a pair of charge EE, right? And you can smoothly connect this configuration to this neutral configuration without breaking symmetry, just by moving around charges. So they basically belongs to the same phase. And you can determine which side you are by just computing the charge at the inversion center. So if the charge is minus E, polarization is 1/2. So basically, the polarization is half of the charge at the inversion center in this example. So this kind of notion is now known as a filling anomaly. So sometimes charge neutrality of the system and point group symmetry cannot be simultaneously respected. So if you strictly impose inversion symmetry, if you start from positive charge, you also have to end with positive charge. Then the total charge in this system is not 0. You see, like we have 1, 2, 3, 4, 5 positive charges and 1, 2, 3, 4 negative charges. So in total, the total charge of the system is E. It means that the edge charge must be 1/2, because if we assume that the charges are localized to the edge, then total charge is E. So just half it. That's 1/2. So this formula assumes that charges are localized to the edge, and also the edge termination has to be designed carefully. For example, if I take this chain starting from negative charge ending with positive charge, the total charge is 0. But if I look at only this part, shaded region, their configurations are the same. So we expect the same corner charge. But you cannot simply divide this by half. But if you strictly impose inversion symmetry, then this is the only allowed configuration. Then you can predict the amount of corner charge this way. So let me give you a concrete example. So a more non-trivial example. So this is like again S equal 1 Heisenberg spin model. So this is Haldane model. But I want to add staggered magnetic field. So I introduce magnetic field, and it is staggered, meaning that it's point up, down, up, down. And this model has symmetry, U1 symmetry. So I want to use this U1 symmetry to define charge. So in this case, it's like a spin, right? Z component of spin. I also have a translation symmetry and inversion symmetry. Then we have two phases. The Haldane phase actually belongs to this polarization 1/2 phase. And in the absence of this staggered field, this Haldane phase and near-ordered phase are distinct. However, because of this magnetic field, actually they belong to the same phase, and they can be smoothly connected to each other. And this product state is actually still different from this trivial state. So this trivial state, you have 0 at every side. So SZ equals 0 at every side, and that's product state. So there are two distinct product states, and they belong to the same different phases, and they exhibit different corner charge or edge charge. So I did some numerics. Like this is the exact diagonalization of the Heisenberg spin chain up to L equals 16 spins. So this is Haldane gap. And if you turn on H, the bulk gap increases, and it never closes, and symmetries are not broken. So this means that Haldane phase and near-order phase are in the same phase, and the bulk near-order starts from 0 and get bigger and bigger as H is increased. Okay. So this is like a special profile of expectation value of Z component of spin for 16 spins and under H equal 1 magnetic field. You see, you have well-defined near order, but that value is not fully saturated. So like this is like a 0.9 or something. But if I compute edge charge, it is quantized already at say like 0.2. So H is 0.2. It's already quantized to 1/2. This is expected value of edge magnetization from polarization. So I explained how to compute polarization for 1D system, right? So you can compute polarization P. So in this case, I took the sum of classical formula plus Berry phase correction, and that is precisely minus 0.5 for any value of H. And but this result is not surprising, I guess, because at H equals 0, we know that Haldane phase supports spin 1/2 degree of freedom at the edge, and if you apply magnetization, it splits. This 1/2 degree of freedom splits into 2 levels, and it induces magnetization. So 1/2 magnetization for infinitesimal H is not surprising in that sense. But we can do same exercise for S equal 1/2 high-dimensional model. So in this case, we don't have SPD counterpart. The H equals 0 phase is gapless. So sorry. So for this numerics, I somehow found a small tiny error. But this is my numerical problem, and so this is gapless space. And once you turn on H, it opens the gap. And I can compute polarization that is quantized to -1/4, and it implies corner magnetization 1/4. Okay, so everything is consistent. So to discuss corner magnetization or corner charge, the SPD counterpart is not necessary. Okay. So let me give you a more precise definition of edge charge or corner charge. Okay. So as I said, U1 symmetry implies the existence of conserved charge, which is given by the integral of charge density, and we compute the expectation value of this charge density operator. So that gives you a microscopic charge density profile. That can be highly oscillating at the scale of say unicell or much smaller than that. So this is not easy to handle. So instead, what we should do is to perform some kind of coarse graining. So here I'm introducing Gaussian coarse graining. So I define a smoothened version of density, charge density, by performing this convolution integral. So basically, sorry, I must have prime here. So the charge density at x is given by some weighted average of charge density at position x prime. When we do so, then this highly oscillating profile will become some smooth profile like this, and we can compute the amount of charges we have at one edge, and that is given by that defines edge charge, right? And also, we can define a polarization that way. Okay, so here, starting from microscopic charge density, I assume that we assume translation symmetry, so it must be periodic function. And here we take some repetition unit rho 0. So I assume that this total charge density is given by the sum of this repetition unit, and this is not unique, but we require that this goes to 0. This quickly goes to 0 as a special function, and also like this is charge neutral. So integral of this rho 0 x is 0. Using this function, I define bulk polarization. So x times density. So this integral is actually like for each unit cell type thing, and I define this. So then we see that this definition of bulk polarization actually reproduces the famous definition of polarization using Berry phase. For band insulators, this rho 0 is given by one-year function. So one-year function squares with some sum. This gives you the this repetition unit of charge density for band insulators. This one-year function is given by the Fourier transformation of Bloch wave function, right, by the standard wave. So what I'm saying is that this definition is same as standard definition of polarization, at least for band insulators, and we can use this this expression for interacting system as well. Then the proof of bulk edge correspondence is actually just some simple calculation. So sorry for a lot of equations here, but this was the charge density profile of infinite system, and for finite system, we assume that charge density is given by this. Just change sum from the from 0 to infinity. So this is like a charge density for semi-infinite system. Assuming this charge density, we can prove that the edge charge is given by bulk polarization. And we know that this is just assumption. You can change surface by surface reconstruction, things like that. but we already discussed surface ambiguity. You can put additional charge or something, but it only changes the integer amount in integer part of the formula. So we are fine. So it's just a calculation, right? So we can do the same thing for higher dimensional systems. So what I do is exactly the same as 1D system. So we take this microscopic charge density, and I expressed it in terms of the sum of repetition unit. So this is the corner, I'm assuming. And I define total charge in the corner in the region R by this formula. And I found that that is given by the sum of three terms. One proportional to the length in this direction, the other proportional to this direction, and something else. And this, W1 sigma 2 part is the surface charge on this edge. And this part is surface charge on this edge. And when they are zero, we can discuss corner charge. And the corner charge is given by not polarization, but this complicated combination of quadrupole moment. So instead of just R or just here X, so X times density, now I have some quadratic function of X, and basically we can just perform this integral to see the quadrupole moment. And we can do the same thing in 3 dimensions. The formula gets more and more complicated, but basically for each corner, we can discuss surface charges and hinge charges and corner charges by computing like this polarization or quadrupole moment or octupole moment. These are fine. However, there's an ambiguity in these formulas. So again, rho zero is not unique. In other words, even for band insulators, I said it's given by one function, and the one function is defined from Bloch wave function. And if we change the phases of Bloch wave function, the spread of one function changes. But the one center, so center position of one function doesn't change, so that gives you polarization. But higher multiple moments changed arbitrarily by changing the phase of Bloch wave function, because the spread of one function is not gauge invariant. So these formulas are only for given Bloch wave function, and they suffer from gauge ambiguity, so it's not useful. So what should we do? Then hints are given by surface ambiguity. So given material and corner charge, we can decorate surface by attaching polarized 1D chain, or say attaching additional charge to the corner. In 3 dimensions, we can attach 2D system with corner charge as well. That changes the amount of corner charge by this amount. So not only bulk formulas are gauge dependent, but also this surface corner charge is also gauge dependent or decoration dependent. So we got gauge dependent answer, but that was fine. Like we are looking at correct formula, and both sides suffers from severe ambiguity dependence. Then we can assume symmetry. So let's talk about C4 rotation symmetry. And then under the symmetry, the polarization of this 1D chain must be the same as polarization of this 1D chain. So this px is actually minus py, and so attaching this 1D chain doesn't change the amount of corner charge. So that way, you can kill many ambiguities in the formulas. And we found that this quadrupole formula actually reduces to this simple formula. So it gives you the amount of corner charge in terms of the U1 charge at high symmetry points. So here I'm talking about C4 rotation symmetry. So this is a unit cell, and unit cell origin have C4 symmetry, and the center of brackets actually have C4 symmetry. And so there are special points in the unit cell, and these special points in unit cell is classified by the notion of Wyckoff position. And this Wyckoff position is listed in this very nice book, International Table for Crystallography. And for each space group, you see what the special position in itself is. Anyway, what you should do is to compute the U1 charge at high symmetry point in the initial. Then it already predicts the corner charge. So in this example, at the Wyckoff position A, you have charge 2, so the corner charge must be 1/2. You can do the same exercise for other symmetries. And anyway, I think the most important point is that the U1 charge Q modulo NE at CN rotation center is topological invariant. So this is like an inversion example, like a charge at inversion center mod 2E was topological invariant. The same way, if you want to change the charge at the rotation axis, you have to bring in charges symmetrically. So it can only change it by charges by NE. So it means, like this is like a real space invariant, and it gives you a corner charge. We can do the same thing for three-dimensional systems. So we found that this octapole formula reduces to this simple formula. Basically, you compute charge at high symmetry point in initial and divide it by 8. That gives you the corner charge. And from this formula, we found that, okay, the most simplest example of octapole insulator will be sodium chloride, because it has charge E plus E at Y position A. And so in this case, the U1 charge Q modulo 2E instead of 8E is a topological invariant. The reason for this 2E is that if you want to change the charge of this point, you can bring in charges from corners as well. But you can also do bring in charges from edges. So the coordination number of this point is actually 6 instead of 8. So this mismatch of 8 and 6 gives you 2E. So actually, what is topological is kind of different. It's a little bit complicated, but anyway, you can discuss that. The U1 charge Q mod 2E at the OH point center is topological invariant. So this is again this discussion. These results are consistent with filling anomaly formula. So what you can do is to compute the total charge in the system and divide it by the number of symmetry-related corners. So in this example, you have 8 corners, and the total charge in the system, if every corner is terminated with positive charge, then the total charge in the system is actually plus E. Then the corner charge must be 1/8. In the previous study, they studied only 2D systems, but the same idea can be applied to 3D system. But as I said, we have to really pay attention to the modulo part. Okay. There's another explanation of the corner charge of this cubic system. You can start from 1D system, this 1D arrangement of plus E and minus E, or NA plus and CO minus. So this gives you polarization 1/2, and it predicts corner charge of 1 plus minus half, right? Then you can understand this 2D system as a decoupled wires or 1D wires, and this decoupled 1D wires have corner charges plus E minus E. So again, regarding this edge as a new 1D system, you can predict 1/4 charge to this 1D system. So that is a corner charge of this 2D system. The same way, you can regard this 3D system as a periodic arrangement of layers of 2D systems, and that gives you the understanding of this 1/8 charge. Okay. So can we measure that? So traditionally, polarization has been measured from actually not directly, but indirectly from the current, electric current. So So people apply electric field, or more generally, people change some parameter in the system and measure the current that flows during the process and compute polarization. But then, like, we need to have some reference system and do some change, like, change your electric field or something like that, and measure current. So that gives you only the kind of change of polarization. So here I want to propose more direct measurement of corner charge. So here, so this is the cube of sodium chloride. And what I want to do is to measure the electric charge localized to this corner. So what I'm proposing is to measure the electric force acting on a test charge placed at distance d from this corner. Oh, sorry, that's coffee machine. I'm sorry. Yeah. So if I measure the Coulomb force, if this point gets too close to this corner, then I must see the individual particle, individual ionic ions, right? So the electric force scale with E squared over D squared. However, once I get far away enough, then I can see the corner charge, fractional corner charge, and that is quantized to 1/8. So I must see some crossover of the spatial dependence of the Coulomb force. That should change from this E squared over D squared shape to E squared over AD squared shape. So by plugging in some numbers, I found that at this this A is the lattice constant for sodium chloride, and the electric force is like this amount, like some 100 piconewton. And I heard that this is not unrealistic number if you use like a AFM type measurement. If the tip is charged, you can measure this Coulomb force. And if you see that this slope is given by this E squared over AD squared shape, then you can see that's a direct measurement of corner charge. Or you can look at the steps that might exist on the surface of 3D system. And the corner of this step must have 1/4 charge. So that might also be measured from this kind of experiment. And we also checked the robustness against impurities. And so today I only explained charged system, but we can do the same calculation for antiferromagnet as well, right? So if spins are up and down and this collinear antiferromagnet, it can be regarded as a magnetic version of ionic crystals. So the corner of each antiferromagnet must have this amount of corner magnetization. There are some subtleties, if we assume that the model is model has spin rotation symmetry, then antiferromagnetic texture originates from spontaneous breaking. Then there are Golson modes, and the system is not gapped. Or if we assume anisotropy, then Euler symmetry is not exact. So there's some trade-off. And so what we computed is, even for isotropic case, in the absence of external field, the corner magnetization is quantized to expected value. And also, even in the presence of anisotropy like this, that the deviation of corner magnetization from the ideal value is very small. And this is what we are currently working on. So this is a summary of my talk. Today what I wanted to do is to clarify the difference between topological insulators or SPT phases and trivial states. And there are some similar bulk boundary correspondence. So higher topological insulators have gapless modes at the hinges or corners. And similar to that, we have higher trivial insulators that have fractional charges on hinges and corners. And these topological sides must have some irremovable quantum entanglement, but these trivial sides can be connected to product states. So it can be realized even as the classical systems. And that is why we think sodium chloride that is a very simple compound can exhibit corner charge. And not only sodium chloride, you see like every ionic crystal must have some kind of signature because it has a periodic arrangement of charge, positive and negative charges. So that must have some kind of multiple moment. It can be a dipole moment. In that case, we have surface charge. But if it's lower, then it might be easier to realize because it's energetically more stable. And it would be nice if we have a direct measurement of corner charge. And you see like so previously, so this is a figure from this Nature article. Previously, people kind of mixed up these two things. So this figure is for trivial multiple insulators, but these figures for topological insulators with gapless mode. But I think the most important message on my today's talk is to draw some clear line between these two and understand the different type of boundary correspondence. Thank you so much for your attention.
Thank you, Haruki. Very nice talk. So, so we'll now open up for questions. So if you have question, you can raise your hand, and I can unmute you, and you can directly ask Haruki your question. So maybe I can ask a question first. So so let me just try to understand this whole story. So you were saying that this polarization has a very nice formula in terms of Berry phase. So these higher order ones, it seems that the result is that there is not a relation to the topology of the band structure or anything. Or did I understand it correctly?
Yeah. So this is like a like integral of charge density. And charge density can be expressed using one-year function. Then you can write down some kind of Berry phase type formula. But using that formula is very difficult because you see, even under proper symmetry, implementing the symmetry to the growth wave function is not that easy. So computing like a polarization, computing quadrupole moment or octupole moment from like Berry phase type formula seems to be very difficult task. And instead, what we found is that it's easier to compute U1 charge as a topological invariant under some symmetry. So this is like a real space invariant type formula. And yeah, I think yeah. So like formulas, polarization. Formula for polarization was in like a like a momentum space formula, right? Berry phase. That kind of understanding is more difficult for higher order multiples. And instead, real space formula works well.
I see. So my naive picture of understanding these corner charges would just be that you mentioned this smooth function that in the bulk of the material, if you take a region and you smooth it, you roughly see zero charge. But as you move to the corner, because part of the region become empty, then you don't have the balancing charges, the neutralizing charges to cancel things out, and you have some remaining.
Right. Residual charge. Yeah.
Okay. I see. So if in that sense, if we don't just have an ionic crystal, if we have some other crystal where charge is not completely moved from one atom to the other atom, do we have some non-quantized? I don't know.
Yeah. So what I'm saying is that non-quantized corner charge are not stable.
Oh yeah.
So you can change the amount of corner charge arbitrarily by decorating surface. So or you can say you cannot predict the amount of non-quantized corner charge from the bulk. So if you have also information about edges, there's a chance. Because knowing the edge, you see you know what kind of decoration is done on the edge, right? So then you have a chance of predicting corner charge, and even in that situation. But that's kind of not bulk corner correspondence. It's like more like a bulk edge to corner correspondence. And there's a nice work by Luca discussing that. So this paper discusses that point, like knowing the edge, you can predict non-quantized corner charge. This Vanderbilt paper is also doing something similar to that.
Thank you. Okay. So do we have questions from the audience? Let's see. Well, if not, I guess we can thank Haruki for a very clear talk.
Yeah, maybe the topic of today's talk is too simple for Caltech people.
It's nice. I have thought I don't have atomic force microscope though. Yeah, thank you.
Yeah, thank you so much.
Yeah, sure.